absolutely imperative that you're writing stuff down to understand what is going on. There is way too much information here, especially these next first few days of this stuff, that it can be overwhelming. And if you're not on top of what we're working through, it's going to bite you in the keister, shall we say. So when we get going into, I was telling this the first hour, this portion of the trig unit really becomes like pre-calc light, if you will. This is really where the preparatory portion of this class gets you guys ready for either honors or regular. It doesn't really matter which one. Either one of those classes, they spend a good chunk of first and the second semester in trig, like when we do second semester. This gets you ready for all of it. By taking the time that we do to go really in depth on why all of it works, how it all is so visual, as you get into the more complicated things towards the tail end of this unit, and then in the next year, you'll be like, oh, that's easy. Oh yeah, I got that. That's no big deal. As you go on. So that's kind of where I hang my hat on the trig unit, because I really think that the way that we present it helps you guys out a lot. At least that's just my own opinion. You guys don't care. But anyway, we're talking about what's called general angles, and we kind of looked at this stuff not too long ago, where we talked about what was called angles in standard position. And excuse me, when we talk about what are called angles in standard position, we're going to start talking about them in terms of the XY coordinate plane. And what we do is we're going to have what's called an initial side. It's up to you how you draw stuff out. What we're going to do is we're going to have coordinate plane. We're going to place angles within the coordinate plane. Angles obviously are comprised of two sides and a vertex. I'm assuming you guys all remember that from last year in geometry. What we're going to do is we're going to place all of our vertices will always be placed at the origin. The initial side where the angle starts is always going to be at the x-axis, the positive side of x-axis. And then for positive angles, it's going to rotate counterclockwise. Okay? Where the angle stops is where what we call the terminal side, this ending portion. Now, your quadrants, your angles can lie then within a quadrant. You guys remember how the quadrants go in the coordinates?
Yeah. Positive.
1, 2, yeah, as you're going, 1, 2, this is 3, and this is quadrant 4. Do you guys know what it's called if you don't land on a quadrant, you land on an axis? You know what that's called if you land on an axis? You guys ever heard that? You never heard that before? No, I know where you're going with that, but there's a term for that. If you land on an axis, it's called a quadrantal. If your terminal side of an angle lands on one of the axes, whether it's 90, 180, 270, 360, or some multiple of one of them, it's called a quadrantal. We're not really dealing with what are called quadrantals today, but then in a couple days when we actually talk about them, you'll at least know what the word means. It just means they're on an axis. Okay, that's all that means for right now. Quadrantals are just if the terminal side of an angle is on an axis. Okay. So, like I said, what we do is we place angles. We start at 0. We rotate around and through. A nice example here would be this angle could be, I don't know, we'll say maybe it's 140 degrees. So if I say that this theta is 140 degrees, it started at 0 with the terminal side, it rotated over. Now, if it's 140 degrees, how far is it off of the x-axis? 40 degrees, okay. Now, this is another term I'm going to start using a lot of. This is called a reference angle. A reference angle is always how far you are off the x-axis. Always the x-axis. Okay, that's kind of an important thing. We're going to talk about it every time we draw an angle, every time we place an angle. I'm always going to ask you guys what the reference angle is. It's not so much important today as it will be as we go forward, because once we start getting used to what it looks like, trigging is going to be easier. Yes, sir?
So if you had an acute angle, would the reference angle just be
If you have an acute angle of 30 degrees, what's your reference angle? 30 degrees, very good.
So 90 degrees is the right degrees, so that would be
90 degrees, yes. What's that? Yep, it's how far you away from the next axis. Because if you're at 100 degrees, aren't you closer to the 180 than you are 0? That's where it goes from. It's the next closest angle. Same thing if I drop down to here, let's say I'm at 200 degrees. How far am I off of 180? 20. Okay? If I'm over down in that fourth quadrant at 330 degrees, how far does it take me to get back up? 30. That's reference angles. How far are you bouncing off the axis? Yes, sir? No, that will never come into play. You will never worry about that. You'll never worry about y-axis location. Or how far you are. Yeah. For this one, yes, because the original theta, I was just guessing, it looked like it was more over this way than it was. I thought, oh, that's 140 degrees, was positive, and went counterclockwise. How much further are you from that? 40 degrees. All right? So the idea is, if I wanted to do a draw, which puts a good one. What's that? If I want to draw 110 degrees, I'm going to draw and place 110 degrees and find its reference angle. Okay? I know in this first section, and I'll remind you guys again later when we talk about some homework problems, it never asks us in this section about reference angles. I just want you guys always to do it, right? Just to get in the habit of it. So if I want to draw 110 degrees and make a grid, 110 degrees, what quadrant does that drop into? Second quadrant, good. So if I start here, bring it over, my terminal side's over here, I label 110, and then how far am I up from 180? 70, boom. That's what I want us to be able to do. Yes, sir? Always go x. Reference angles are always to the x-axis. They never go to the y-axis, ever. Okay, let's go. There's a reason why we're drawing. There's methods to why we start doing it this way. Okay? Trust me.
Is there something different when we're finding it off the y-axis?
Never. Once again, you will never find off the y-axis. Unless you, well, no, that's not even this. Never mind. All right. What if I did this? Let's say negative 150. What direction do I go now? Clockwise. Right. You did it like that because it's negative. Remember how last year we said there's no such thing as a negative angle?
Now there is.
Now there is. Negative angles do exist. They just go in different directions. You don't have negative value of angles, but you could have negative You can have a negative angle because it's just a different direction. Okay. It's the same idea of why we don't talk about distances being positive, because you're still walking some distance. I'm just walking backwards. Okay. You're still moving some distance. Angles, if it's negative, they go clockwise. 150 degrees. That means I'm going to go to about here. How far am I now off of the x-axis? 30 degrees. So I'm negative 150, but I'm a 30-degree reference angle. Reference angles will always be positive. Bless you, because think of the reference angle. The reference angle is how far are you from something. Reference angle is, in fact, distance.
So it's an absolute value.
Yeah. Yeah, reference angles will never be negative. Because you're that far off of it. You're 30 degrees away. You're bouncing.
Will you have a negative that's greater than 180 and crosses into the positive?
Yes, sir. It's still a negative angle. Bless you. It's still a negative angle. For example, if I say negative 220, okay? If I go negative 220, it's still a negative angle, and it comes up past 180. How many degrees past 180 does that go? 40. So it's still negative 220, and it has a 40-degree reference angle. Yes, sir. Yep. Yep. And you're getting to what are called coterminal angles. We're getting to that. All right. So far, so good. Just spin it to win it, if you will. Okay. It's just a matter of counting how many times you go around. Now, the other thing we get into is I'm really not giving him my notes beforehand. Is labeling these things out. Is the idea of what is called a coterminal angle. Coterminal is, if you think about the terminal side of an angle, it just means they share the same ending spot. So if you have coterminal angles, they share the same end spot. For example, if these here right now. If we have, excuse me, we'll make it really easy. If I say this is 100 degrees, if that's 100 degrees, and for right now, I'm not going to worry about reference angle because it's just going to get a little messy for my point here. How many degrees does it take me to get back to the same spot?
360.
360 degrees. Because you say 180, if I went 180 from here, wouldn't I just be down here? Okay. So if I go around again, I'm in the same position. How many degrees is that? 460. Good. That's 460 degrees. Okay. Now, if I go and I want to get, bless you. Let's say I want to find a negative coterminal. I go the other way. I would start here and come up to here. It would be what?
Negative 260.
Negative 260. Very good. It's just going the other direction. Negative 260 degrees, positive 460 degrees, and 100 degrees all share the same terminal side of theta. They all wind up in the same spot. Bless you.
Thank you.
It's like 3 rights and a left. Yeah. No. A little left. Stand up.
4 rights.
Oh.
4 rights.
No, that
Here, everybody stand up. Stand up. Stand up. All right, stand up. You bum. I did. So everybody turn 90 degrees to your right. Turn 90 degrees to the right again. Turn 90 degrees one more time to your right. Are you facing left from your original position?
Because I went one.
See, now you know how to make a left in Michigan. There's no left-hand turns in Michigan like anywhere.
There's really, and there's no streets on it.
That's just
That's right. What's the term? Yeah.
Michigan is worse.
Everybody okay with this so far? Positive, negative, coterminal. What happens is there's some rules that go along with positive and negative coterminal angles. Basically, in order to find them, I don't know if you noticed this, to find them, there's 2 things that can happen. Well, let me put this on clean. 1, if your original angle, excuse me, is within 1 revolution. Okay, when I say 1 revolution, 0 to 360 or 0 to negative 360. Okay, within 1 revolution, positive or negative. All right, plus or minus. All you have to do is you add 360 and you subtract 360 to get the other coterminals. If you notice what we did there, we had the 100 degrees. We added 360, wound up at 460. We had the 100 degrees, we subtracted 360, we wound up at negative 260. You add and subtract a multiple, or you're adding and subtracting 360 if your original angle is within 1 revolution. Okay. This works if it was a negative angle to start with as well. If it started with a, let's say we were at negative 80. This makes it easy. If my original angle is negative 80, I'm in the 4th quadrant. Okay. My reference angle here is 80 degrees. That's how far I am off of the x-axis. Yes, sir. I'll show you in a second. Okay. So to get the positive of this, I would add 360. So if I add 360 to negative 80, what do you get? Right, so your positive would be 280. Okay, if I go more negative, I'm going around again. 60 wouldn't it be? It's negative 420, right? 80. Yeah, it's be negative 420.
Oh, that's one.
So there's your positive. There's your negative. Even though you started negative, you still have a positive and negative coterminal angle. Okay. Since that negative angle, the original angle, was within 1 revolution, all I have to do is add and subtract, and I'm right at the same spot. Okay. Now you're worrying about what happens if you're going around them. Okay. Stand up again. Oh no, let's make it safe. Turn around once. 1 full revolution. Okay. Where'd you wind up? Okay. Go around 3 times. Where'd you wind up? So, does it matter how many times you go around, you can still be in the same spot. So if you go around 360 degrees, is it 360, 720, and then what? 1080? 1080? Is 3 times around?
Yeah.
So if you wanted to get a positive and negative coterminal, if you're beyond 1 revolution, you have to back yourself into 1 revolution to get it there. Okay? And that's the weird one. So the second version of this is if you are beyond one revolution, you backtrack to get within 1 revolution. It sounds more complicated than it really needs to be. We'll make it really easy. For example, let's say that we are at 400 degrees. 400 degrees is more than 360 degrees. Do you agree with me on that?
Yes.
So if I spin it around, I go around once, and then 400 degrees would put me in the first quadrant. How many degrees up off the x-axis? 40. Okay, good. So here's my reference angle, 40. All right. So in order for me to get within 1 revolution, since I'm beyond 1 revolution more, I subtract 360. So my positive coterminal angle is at 40. And then I do that again to subtract 360 again to get my negative coterminal angle, which would be at negative 320. So all you're doing is you're either backing out 360 to get within it if you're above, or if we started at negative 400, you'd be adding 360 to get to it.
So you add, or you subtract 360.
So you get there. Yeah. So if we were at the 3 times around, you backed out twice, and you get within. So if I actually go 3.5 times around, you'd go around and you hopefully don't puke, and then you back yourself out, and you're within you're at pi, or it's 180, and then you would have the other one again would be at negative 180.
And you fall over.
Yeah.
Hammer. I feel like we're going to
So-
be spinning around a lot on this one.
Not really. I mean, it's just a matter of referencing and seeing where you wind up. Okay. Positive, negative coterminal angles.
Okay.
We did the coterminals, we did this, did this, did those. Now the fun stuff. Ratings. This is what you guys have all been looking forward to. So, the button that I always told you not to worry about, don't worry about it. Seriously. There's a reason why we never worry about the button, because there's a conversion that occurs in terms of how angles are measured. Radians are just another way of measuring angles. So, let's go back and let's draw another XY grid. And, excuse me, I don't know why you're taking calculus out, we're not using them.
That's why you said don't worry about it.
So, you guys are okay if we start at 0, we go all the way around, we wind up at 360?
Yeah.
Yes.
We're going around something, right? Okay, so I'm just going to put a little circle in the middle, circle in this. All right, so I start at 0. I go all the way around, I wind up at 360. Be okay with that?
Mm-hmm.
What's halfway between those two?
180.
Good.
That's horrible.
What's halfway between 0 and 180?
Now 90.
Okay. So I go 0, 90, 180. What's down here? 270. Good. So to get around the circle, we go around 360 degrees. Now, that's if we're going around an object, we're measuring circumference, isn't it?
Yep.
How do you find circumference?
2 pi 2.
2 pi r. Okay. Now, in this case, you're right. Circumference is 2 pi r. It's the distance around the circle. The radius is basically arbitrary depending upon how big or how small the circle is. It just has that multiplier of the 2 pi to it. So for us right now, I'm going to say our radius is 1. So if I start at 0 and I go all the way around the circle, go all the way around the circle, where do I wind up at? 360, but instead of 360, I start at 0. If I'm talking about in terms of pi, I wind up at 2 pi.
2 pi.
Okay. So if I start at 0,
So 180.
180 is 1 pi, because what's halfway between 0 and 2 pi? Pi. What's halfway between 0 and pi? Half a pi. But we don't write half pi, we write pi over 2. Okay. Now, think about the way the fractions work. 0, 1 half, 2 halves, 3 halves, and then what's back at 2 pi? 4 halves, which is 2. Are we okay with this so far? Okay. What's halfway between 0 and 90? 45. So 45.
4 pi.
Okay. So then if I go 45 here, 45 here, 45 here. So let's see here. You said 45. So 0, 45, 90. What's 90 and 45? 135. 135, 180, 225, 270, 315. You okay with that? I'm just adding multiples of 45. Now you guys already started getting ahead of me here. 90 is pi over 2. 45 is half of 90. Well, half of pi over 2 would be pi over 4. Because half of a half is a fourth. So pi over 4.
And you can keep going for every.
Yeah, they'll count it because you know these increments are all the same. So this is 1/4, 2/4, 3/4. This is 4/4, 5/4, 6/4, 7/4, 8/4. So far, so good? All right. Now, we have 0s, 90s, and 45s. What are the other two angles we always dealt with last year? 30s and 60s, aren't they? Okay. So if you think about it, isn't 30? If I go up 30, then I go up to 60, then I go to 90, 120, 150, so 30, 60, 90, 120. It's okay, you don't have to draw it all out right now. We're gonna do this again. There's more to this. Okay.
Oh, okay. This is
210. I'm just gonna show you guys how the relationship works here real fast. 210, 240, 270. I'm just going up by 30s, 300, and then 330. Everybody okay with that? Careful. 30 is how much of 90? 1/3. What's 1/3 of 1/2? 6. So each 30-degree increment is 1/6 of the circle. So the first one would be pi over 6. 1/6, 2/6, but 2/6 is 1/3, so pi over 3. 1/6, 2/6, 3/6 for half. 4/6, which is 2 pi over 3. 4/6. Oh, sorry, I put the wrong spot. The 120 was here. 5/6. 6/6, which is 1. 7/6. 8/6. 9/6, 3 halves. 10/6, 5/3, and 11/6, because 2 pi would be 12/6. So what's happening here is what we did is we converted our normal degrees that we've worked with into radians. You guys actually did this a lot last year when you did arc length. Remember that?
Yes.
Sort of. When you did arc length. Arc length was the distance on the circle, right? Part of the circumference. Isn't this part of the circumference? 30 degrees is 1/6 of 2 pi, or 360. 30 over 360 would be 1/6, wouldn't it? That's where this comes into play. So what you guys did last year is you guys did arc length. You did central angle over 360 times 2 pi r. Does that vaguely ring a bell?
Yes.
All right. Now, when you did this, your radius was always arbitrary. It could have been anything. What's my radius right now? It's 1. So does this r value matter? No. Your central angle was always in degrees, wasn't it? Okay. So what we did is we multiplied our degrees times 2 pi over 360. Well, you guys probably didn't simplify this right away, did you? Because 2 over 360, doesn't that just become 1 over 180? So this basically meant angle times pi over 180. And that's how you converted from degrees to radians. You were in radians as soon as you started putting things in terms of pi last year. You just didn't know it. Okay? Bless you. So to go from degrees to radians, you take your degree times pi over 180. That's how you convert. So if I wanted to do 100 degrees in terms of radians, it would be 100 pi over 180. And then I simplify it.
Pi over 18.
Yeah. Okay. All right. Again, if I want to go 100 degrees, I multiply it by pi, divide it by 180, and I get pi over 18. No, it's not 18. It's not 18. Sorry. It'd be 5 pi over 9. Because 0's dropped and it's 5 over, yeah, so 5 pi over 9. Sorry. Got ahead of myself there. You owned it. You sold it. I bought it. All right. That's converting because radians have pi in it. Now, what do you think you have to do to go the other way?
Well, 180 over
180 over pi. Because do degrees have pi's in it? Nope. To go the other way, let me split this over the question. To go the other way, go from radians to degrees. We take our radian value, whatever it is, radian times 180 over pi. Whatever it is, whatever that theta is. Because what will happen is the pi values will drop. Because pi divided by pi was always going to equal 1. So if I happen to have 7 pi over 3, and I want to convert that to degrees, I multiply it by 180 over pi. Pi's go away. 3 goes into 180 how many times?
60.
60. What's 7 times 6?
440.
And then add a 0. Oh, yeah, sorry, you guys already had me, sorry. And that's how it would work. It's quick and easy, going back and forth between degrees and radians. Okay. Now, can I do coterminal reference angles and all that stuff in radians as well?
Yes.
Absolutely. Instead of adding and subtracting 360, what am I adding and subtracting? 2 pi. Okay. So if I wanted to get if I wanted to figure out what my reference angle was, let's do an easy one. Let's say 2 pi over 3. 2 pi over 3. I'm just saying that's my angle. Okay, I'm gonna place it, I'm gonna draw it, place it, find the reference angle, and then get coterminals for it. Positive and negative. Do the whole shebang for this one example. Yes, sir. Yes, sir. So if I'm starting with 2 pi over 3, the first thing I do is draw my graph. And I want you to start thinking, 2/3. Is that more or less than halfway? In this case, because my numerator is smaller than my denominator, I know I'm not in my second or third quadrant, third or fourth quadrant, because I know it's positive. But yes, it's beyond, everything okay? It's beyond halfway, so it's got to be beyond pi over 2. So if you think about it, how many more thirds do you need to make a whole? What's going to be your reference angle? Pi over 3. So my reference angle here would be pi over 3, because this is 2 pi over 3. It drops you to the second quadrant. Right? Now, if I wanted to get a positive coterminal angle to this, I needed to add 2 pi. But I don't want to add 2 pi, I want to add it in terms of thirds. What's 2 pi with the denominator of 3?
6 pi.
6 pi over 3. Okay with that? Working. Remember, because you have to add and subtract 360, but instead of adding and subtracting 360, I'm going to add and subtract 2 pi. But I need to do it with the common denominator. So 2 pi with the denominator of 3 would have been 6 pi. Right? Remember we did a little bit of this before with some of the rational stuff? We were trying to do the common denominators real quick. This is why we did that. So we can do common denominators real quick. So I would add 6 pi over 3. So I would go around, and I would wind up at, well, that would be 8 pi over 3. Same reference angle, same everything there. If I want to go negative, again, if I'm going negative, think of it in terms of negative pi. I'm moving negative 3 pi over 3, and then I have to move up another 1/3 pi. So my full on would be negative 4 pi over 3. Okay? Adding, subtracting 2 pi to it. If you know your reference angle, you know how much of a pi you need to go up or down to match up to it. That's where reference angles are super important.
Why isn't it 6
Why is it 6 pi over 3? Oh, what's 6 over 3?
Oh, it'd be 3 though.
Yeah, 360 is 2 pi. Because remember, I'm adding, subtracting one reference. Okay. Come on. Okay. Yeah, I always, whenever I know I'm going to add 2 pi, this is 2 pi, I'm just making it easier on myself. Okay. Now, remember I also said that mixed numbers are stupid?
Yes.
Guess what? Mixed numbers are awesome for this. Okay. For example, let's try, trying to think of one would be easy to work with. 17 pi over 4. 17 pi over 4.
So 4 over 4.
So it's 4. Right, so again, 17 over 4 is what is the mixed number? 4 and a fourth. So this is the same thing as saying 4 and then pi over 4 for 1/4 pi. We okay with that?
Yeah.
So was it a positive or a negative angle to start with? Positive. So is this above or beyond 1 revolution? Beyond. So we have to bring it in within 1 revolution, don't we? How much is it beyond the revolution? Well, whoa, is that 4 times around? 2 times around. And that's the trick. So when you're counting via pi, this is where it gets to be fun. Ready? 1 little, 2 little, 3 little pies, 4 little. So I went around, I'm counting pies as I'm going. 1 pi, 2 pi, 3 pi, 4 pi. Go by, bring it down to smaller chunks. All right, and you're going, 1 revolution is 2 pi. So then I come up, pi over 4. Isn't that first, like you said earlier, Jared, when I'm in that first quadrant, isn't that my reference angle?
Yeah.
So what's my positive coterminal angle? It's the reference angle, it's pi over 4. So basically what I did is I backed out 2 pi twice. Yes, sir?
Would you think it'd be more useful to put it as, write it as 4 pi with pi over 4?
You can do that if you want, that's fine. That's perfectly fine, because you're not doing anything with it, you're just counting how many times you're going around. As you get used to it, you're never going to write it down more than once. Okay? So we just went around, wait, I'm coming the wrong way. Went around 2 pi, 4 pi, up a quarter. So there's my positive. Now to get my negative, I'm coming this way. Well, if I'm going negative, 1 full revolution negative in terms of fourths would be negative 8 pi over 4. But I'm up how much? 1/4, so how much, what's my negative then?
Negative 7 pi.
Boom. Yep. It's really easy because it's so visual. The negative was, because remember I started, I know my reference was pi over 4 for the positive. Because as soon as you get into your, once you back out all the revolutions and stuff like that, once you're within one revolution, there's either your first positive or your first negative, depending upon what you started with. We started with positive, so that pi over 4 is within one revolution, so that's my positive. And then I do it the other way, and I get my negative. Yes, ma'am. Because isn't pi over 4 1/4 off the whole revolution? And the whole revolution, and going the other direction, is negative. So that means you had to back out the 1/4, so we got the 7. Yep.
So it's positive with the number.
Yes.
Okay, and then, do you use the denominator or whatever you're doing?
Yeah. Yeah, it usually doesn't simplify. They'll usually give something that won't simplify. Okay. All right. Okay. Let's try it. Hate trying to do this on the spot. Oh, here, we'll do this one. Do 11 pi over 4. Actually, let's do it this way. Let's do negative 11 pi over 4. I want to get a positive and a negative coterminal angle off of that. Let's change it. So we just did a fourth. Let's do a third. Let's do negative 11 pi over 3. Let's do positive and negative coterminal angles. Negative 11 pi over 3. All right. Whole fractions here so much. It's negative 3 2/3 pi. Are you okay with that?
Yeah.
All right. Now, when you have an odd pi, all right, so an odd whole number, that means it's not a full revolution. It means you're over in one of the, you're either going to be off between 2 and 3 quadrant. Okay. So you look at it. This is where it's about 1 little, 2 little, 3 little pi's. That got me to the 3 pi, negative 3 pi. Now I move up 2/3. Is that 2/3 beyond or below halfway? It's beyond. It goes to the first quadrant again. So here, how far is the 2/3 off of the x-axis? 1/3. So my reference angle here is pi over 3. Now, isn't that my positive coterminal angle? Yep. That gives me my positive coterminal angle. Now, to go all the way around negative in terms of thirds would be negative 6 pi over 3. Are you okay with that? I'm up 1/3 of it, which means where am I at? There you go. Negative 5 pi over 3. So to come back around, that would be negative 5 pi over 3. Yes, sir. And what's that? Well, we didn't have it. Because it placed you into that quadrant. Once you pop into the first quadrant, you have your positive. If it's within one revolution, then it gives you your positive. It's just an easy way to do it. I'm really surprised that most textbooks don't introduce the idea of reference angle when they do this. Because using the reference angle to help you figure out how far you're bouncing stuff just makes so much more sense. That's just, in my opinion, that's why I always present it this way.
And if it only comes into the second quadrant.
Then you're up here, so you gotta figure that out. Okay. I don't think I posted it yet, but I know the PDF is up there. I want you guys to do number, it's on page 780. It's gonna be 28 through 58 evens. So, page 780, 28 through 58 evens. The first couple of questions talks about drawing the angle. Whenever you draw an angle, whenever you do a coterminal positive or negative, please make it a point to always find your reference angle at the same time. It doesn't say to do that, but this is one of those add-on things that I always want you guys to do because it's such tremendous practice to do so. Using reference angle is what's going to save our butts as we get going into the fun stuff. Yes, ma'am. Yeah, but what happens if you're over here? You still have to. I mean, even if this wound up in this quadrant, I just want you guys to figure out how far are you off the x-axis. Just get in the habit of finding that. So if this happens to be, I don't know, 5 pi over 4. Wait, no, that would be over here. 3 pi over 4. How far are you off the x-axis? 1/4, right? So it'd be pi over 4. If you were down here and let's say this was 7 pi over 6, how far are you off the x-axis? 1/6, so pi over 6. That's what I'm just trying to get you to the habit of finding that out as well, whatever the reference angle. Even if you just put it off the side, because not all the numbers are going to be as clean. I think the first one is 144 degrees. The first problem here says 144. 144 goes to what quadrant? Second quadrant, okay? So I would draw here, put my terminal side, label it as 144. How many degrees is that up from the x-axis? 36. 36. So that's what we're trying to do.
So 36 would be your reference angle?
Yes, sir. 36. Yep, 36 would be your reference angle for that. Okay. You'll find out real quick, our reference angles are only going to be one of 3 again, eventually.
Can you go back to the big circle?
Sure. Yeah. Don't worry so much about this one right now. We're going to rebuild this as we get into the little bit more information that we're going to learn on Friday. Okay. This was just the first idea. I wanted to show you guys the relationship between how you converted from radians to degrees. We knew that 360 was 1 full revolution in terms of 2 pi while we were on the circle. So half of it. And then how did that work with the fractions? It's 11 pi over 6. Yeah, this would be 11 pi over 6. Sorry, because remember that's 60 degrees off, so it's 1/6 off. So it'd be 11. Don't worry. When we go back to rebuild this one on Friday, I have a larger sheet, and then we'll put in coordinates. We're gonna do a whole bunch of stuff with all of it right off the bat to show how the reflections and everything work. This is never anything that I make students memorize because it's stupid. Because everything in the first quadrant reflects to all the other quadrants as you go through. If you understand how reference angles and x's and y's, which where is positive, where is negative, everything's really easy to work with. Okay? And as we get along, like I said, your reference angles are only going to be one of 3. Gee, I wonder what 3 angles they could be. What angles did you guys learn so much about? Geometry.
30, 60, 90.
So 30, 60, and the 145. Because if it's 90 or 180, 270 or 360, where are you landing? On an axis, which means it's what we call those now? Quadrangles. They have their own rules. Right, we'll get to it. All right, we'll get to it. Radians, trig stuff is great. Trig stuff is fun.
What's it called when it looks in pre-calc when you're doing stuff and it looks like the top of the earth with the longitude and latitude lines? I don't know. I mean, last night. It looks like what the earth looks like at the poles. When you have your
He's doing polar coordinates.
Okay.
Polar coordinates. Yeah, they did a little bit of that after some trig stuff. Yeah, so for the rest of the semester, we've got trig. We'll be doing trig stuff up to spring break. Then we come back from spring break, we'll finish up. We'll probably do all the graphing after spring break. And then after that, we'll do conic sections. And then we'll do sequences and series and probability. Conics, sequences and series and probability are all about a week and a half, 2 week units. The trig one is the one that takes the longest. Okay, is 2 nights more or less? So, if you think of it, 9 is What is getting in 7th year, undertaking or year anti. Because you don't have to study full on perfect. It's where's the place. Thank you, ladies and gentlemen. We'll see you guys tomorrow.